Okay, so still in 1.1, but we will finish it rather quickly. Not much to do, but just two more definitions to tell you about. I'm going to be talking about symmetry. There are two kinds of symmetry that we care about. Symmetry is, of course, just the property of a function to be self-similar. Right? So one part of the function looks exactly like the mirror image of another part of the function. There's what's called even symmetry, exhibited by even functions. Right, so that's the subtopic. So we say f of x is even, or an even function, if you replace all x's with the negative x, you get exactly the original function back. So, for example, f of x equals x squared is an even function, since if I take f of minus x, that's just minus x squared. This is just x squared, which is the original function. So replacing all x's with negative x makes no difference in the function. We call such functions even functions. Even functions are symmetric about, well, what would you guess if you know that x squared is an example of an even function? What would it be symmetric about?
The y-axis.
The y-axis. Right, so for example, if you look at x squared, notice that if you use the y-axis as a mirror, you take the right side, it flips and it lies exactly on top of the left side. You also look at a function like this. That's an even function. The right side is the mirror image of the left side. These are called even functions. And you can prove that an even function is even by taking advantage of this example, this equation. Replacing x's with negative x's make no difference. Now this is especially useful for talking about trig functions, like something like cosine. We can use this property to our advantage, but we won't really be doing trig functions in this class. But it's also important when it comes to integration. We might cover that later on in the semester, maybe, maybe not, but for now that's what an even function is. Something that has symmetry about the y-axis. The name sort of comes from, the generic examples are x to raise to even powers. Those are even functions. Similarly, there's something called odd functions. F of x is called an odd function. Not if it's strange, but rather if when you take the negative of, replace all x's in the function with minus x, you actually get the negative of the original. So that's the important defining equation. The example would be one example. X cubed is an example of an odd function. Since if I take f of minus x, this means I put the negative where the x was, which that's minus 1 cubed x cubed. That's just minus x cubed. And that's the negative of the original function. Odd functions are symmetric about, do you know how we describe the symmetry of an odd function? Yeah?
The origin.
The origin. Okay, so you look at something like x cubed, the graph looks like this. the idea of symmetry about the origin means if you use the origin as a pivot point, you take your hand over the, for example, the first quadrant. If you rotate that 180 degrees, you get the other part, right? And this is done for each quadrant. So anything in here would be rotated in here, anything here would be rotated in here, and so on and so forth. You say you're rotating about the origin. Another way you can get it is if you take the right side, flip into the left, and then flip into the x-axis, you will get the other side. These are called odd functions. Sine of x is a very famous example of odd function as well, but we won't cover trig. The nice thing about odd functions is if you're taking an integral over a balanced interval, the answer is always 0. But we'll talk about that when we get to integration, which is all the way at the end of the semester. So right now, just use the description, but we won't really be doing a lot with this until like down the road. Know that it is possible to be neither. So, for example, if I take the function x cubed plus 1, that function looks like this. You'll notice that if you flip in the y, you don't get the other side, as well as if you rotate around the origin, you don't get the other one. And on top of that, if you take f of minus x, you get minus x cubed plus 1, which is negative of x cubed plus 1, which is neither the original function, it's also not the negative of the original function. So you can actually see that from the graph, or actually just do the computations. So that's symmetry. We might see that again depending on how far we get on the last topic. The last thing I want to talk about in this section is characterizing increasing and decreasing functions. And we'll come back to this when we learn about some calculus, differentiation in particular, and we'll have another characterization because of this, but I want you to kind of start to get the idea in your head. We say f of x is increasing on an interval I if f of x2 is always bigger than f of x1 whenever x2 is bigger than x1. Sounds sort of confusing, but basically this is what it means. If we were to draw a picture of that, what that means. Say we have a graph, here's x1, and our x2 is bigger than x1. Then the output of this guy, our f of x2, should be bigger than the output of this guy. So in other words, we say a function is increasing if it goes up as you're moving from left to right. One thing you can note, if f is a straight line, it is increasing if it has positive slope. This is actually a very important idea we'll come back to later. You'll see why it's so important when we get to it. Just knowing that a straight line, if it has positive slope, it's increasing. Believe it or not, half of calculus is developed based on the idea of the slope of a straight line. So we are going to review straight lines and finding slopes and what they mean as well. Decreasing simply means the opposite. You're moving down as you go from left to right, and if you're a straight line, you have a negative slope. So I can just, I'll write that down. write it down together to make sure that we're all moving at the same pace. F of x is said to be decreasing on an interval I if f of x2 is actually less than f of x1. For all x2 bigger than x1 in I. i.e., the picture would look like this. Your x2 is bigger than your x1. The output of that value, f of x2, must be smaller than the output of this value, f of x1. And so you're moving down as you go from left to right. If f is a straight line, it is decreasing if it has negative slope. So these are sort of just definitions. It's not particularly something you have to calculate or work out or understand. It's just a definition. You should know what it means when I say, oh, the function is increasing, or oh, the function is decreasing. We're going to be saying that a lot throughout the semester, and I want you to have a picture in your head or an idea of what that phrase would mean. And now we've completed 1.1. So the homework for 1.1 is due on Tuesday. And you will also have a quiz on Tuesday on all the material that I cover up to the end of this class. Any questions so far?
What if it's like going up and then it flattens out and then goes back up?
Oh, that the definition talks about certain intervals. So you'd have to describe it on an interval by interval basis. You have to say, on this interval it's decreasing, then on this one it's constant, then on that one it's decreasing, or you'll actually break it down, right? You can't have a function that's doing both at the same time, right? So you kind of break it down into gaps. So if you have a function that's doing something like this, then that, then that, then that, then that, you'll say it's increasing here. All right, let's actually put in some numbers here. This is something that we'll be going over, but just want to know. Let's say this point here is A, B, C, D, E. You would say it's increasing on AB union CD. And then you'll say it's decreasing on DE. You can say it's constant on BC union. Try to put it down here. FD. Right. So you'd actually split it up, right? But yes, looking at a function in terms of where it's increasing or decreasing is going to be very, very important. But these are the definitions of what that means. And it goes by a certain interval. So you break it into pieces for where it's increasing and decreasing. And just that idea has so many applications you won't believe. We're going to actually talk about some of them in this class. One thing you're going to learn in this class is the power of taking a very simple idea to its far-reaching conclusion. Like if you really sort of abstract an idea and then try to apply it to a general principle that you haven't applied it before, all the nice little goodies that can fall out will be amazing. So yeah, like calculus has two main parts. There's differential calculus and there's integral calculus. And it can get quite complicated, but half of it, differential calculus, it is all based on what we know about a straight line, the whole thing. we start by just, okay, here's a straight line, here's how we find the slope, this is when it's increasing, it's positive, decreasing, negative, and boom, half of calculus. You can actually derive from that fact. And you're going to see that because I'm actually going to do it for you in this class. But in the meantime, you just need to understand the basics. So that ends 1.1. We're moving on to 1.2. Again, basics, but I need to make sure that we're all on the same page here. Nothing new here, just review. Talking about combining functions, ways that we can combine functions. Meaning adding functions together, subtracting functions, multiplying functions, dividing functions, making composite functions, that sort of thing. Most of you know most of what I'm talking about, but it's going to be good to review. So it might seem boring, some of you might be rolling your eyes at me, but it's important. Because I actually caught someone in my earlier class on one of these ideas. So you might think certain things are basic, but when you're doing many basic things all at once, some slip out every now and then, right? If you're doing 5 basic operations, the third one you might have a brain fart and things will slip out. So you really want to be careful. That's how it's going to be. Okay? Another general principle that you want to learn in this class is complicated problems are really just a bunch of simpler problems. So you really want to know the basics so that when you're faced with something huge and complicated, you break it down into little itty-bitty steps where each of those steps are not complicated. Okay, so we need to know the little itty-bitty steps. So the idea is functions can be combined to create new functions. We do this through what we call function operations. Which will be analogous to well, almost analogous. There's one that's kind of strange. Analogous to arithmetic operations on numbers. Okay, so let's say we're given f of x and g of x. Then we can, here's one sort of operations we can do on a function. One, we can add and subtract them. So you can create a new function, what we can call f plus g or f minus g. And its definition is simply you add the outputs. So given two functions that I already know how they're defined, I can define the sum of these functions by simply taking a new function that takes the old functions and then add the y values. Or subtract the y values. So for example, let's say f of x is equal to 2 minus 3x plus x squared. G of x is equal to 4 plus 2x plus 4x to the 5th. Then I can add these two functions. Or subtract, but I'll show you an example of that again. I can take f plus g of x, and that will simply be 2 minus 3x plus x squared plus 4 plus 2x plus 4x. How do we add two functions? What's the principle? Or the idea?
Combine.
Yeah?
Combine like terms.
Combine like terms is the basic idea. So you're going to look for, and like terms are just components of functions. Terms are guys that are separated by pluses or minuses. So this is a term, that's 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 a term. Like term means they're the same except for the coefficient, which is the number in front. So in this case, we have two like terms that don't have any x's on them. That's the 2 and the 4. Those we call constants. So you put those constants together and you're going to combine the constants. Plus, you'll have all the guys that are connected to x's, right? These are the x terms. That would be here the minus 3 and the 2. Then you can combine all the terms that have x squared, the x squared terms. And that's just this guy, 1 x squared. Then you can combine all the guys that have the x to the 5th term. That's 4x to the 5th. And so you can simplify 2 plus 4 is 6. Minus 3 plus 2 is minus 1. That's just 1. You can just write as x squared. And that's just 4x to the 5th. And that is the function f plus g. Note. You obtain this by combining like terms. And like terms mean terms that differ only perhaps in their coefficients. That's our definition of like terms. Another operation we can do on f and g is we can multiply. So we can define fg of x to be f of x times g of x. What's the main principle when multiplying functions? The main principle when adding or subtracting functions was combine like terms. Well, how would you describe the main principle of multiplying functions? What is the main math rule that you're using? Yeah?
You have to FOIL in a way.
FOIL. Well, it's more than just FOIL. It's the general term is using the distributive law. FOIL is just when you have two things in each pair of brackets, but you can extend it beyond. But it's the same idea. We do this using the distributive law. In the case where f and g have two terms only, that's called FOIL, for first, outer, inner, last. It's just a mnemonic to remember the things you multiply, but it's just the distributive law. Then you sum the terms, which is applying the previous operation. So let's see an example of that. So here f of x is equal to x plus 2, g of x is equal to 2 plus 3x minus x squared. This means that I can take f of g of x, and that is going to be equal to multiply, I have to put the functions in parentheses, x plus 2, 2 plus 3x minus x squared. And how we actually compute that is using the distributive law. The distributive law tells us that we have to take each term in one pair of parentheses and multiply every term in the other pair of parentheses. And then we add these all together. So I'm going to take the x, multiply by that, multiply by that, multiply by that. Then I'm going to take the 2, multiply by that, multiply by that, multiply by that. The laws of exponents take effect. So for example, if I multiply an x and an x, the power here is 1, the power there is 1. I add the powers and I would get x to the power 2. So here I would take x times 2, that's 2x, plus x times 3x, that's 3x squared, plus x times minus x squared, that would be minus x cubed, plus Now I've exhausted everyone in that bracket. I've multiplied everyone by x, so I move to the next term. 2 times 2 is 4, plus 2 times 3x, 6x, plus 2 times minus x squared is minus 2x squared. And now we combine like terms. So let's see if there are any constants. So there's a 4. That was the only constant, so I write that down here. Plus, let's see if there are any x terms. I have 2x plus 6x. That's 8x. Let's see any x squared terms. I have 3x squared minus 2x squared. That leaves me with 1x squared. And my x cubed term is just minus x cubed. And that would be the answer for f times g. Questions? You can divide functions. Now there are a lot of mistakes that can happen here, so I'll spend a little bit more time on division. Definition. We can define f over g of x to be, just take f of x and divide it by the function g of x. And of course we'd assume that g of x is not 0. This function is not defined with the denominator 0. It would not be 0. Things to note. 1. In this formulation, you can, what we call, expand along the numerator. There will be cases in this class where a simplification like that will be necessary to apply certain rules. What I mean by that is, let's do it. If I have something like, say, 2x cubed plus 3x squared minus 7 x, whatever. And I'm dividing that by another function, say x squared. I can expand along the numerator. This means I could do something like this. I can split this fraction up into a bunch of pieces where I put each term in the numerator on top of one of the pieces. In other words, I'm employing the fact that a plus b all over c, I can write that as a over c plus b over c. I can expand a fraction across the numerator. Right? This would therefore simplify into 2x. These would cancel, that would give me a 3. This would cancel that, that would give me a 7 over x. Very typically, we will want to write that in terms of powers, and so we write it like that. So when you're dividing two functions, you can expand across the numerator. What about the denominator? Second thing to note is you can not expand across the denominator. A lot of times students see this complicated fraction in a test, they freak out, they don't know what to do, and so to make everything look nicer, they just expand along the denominator. That is not something that you can do. So make sure you tell yourself, this is not something I can do. So for example, i.e., basically what I'm saying is this rule does not work in the reverse. So if I have something like a and I have two terms in this guy, I cannot say that's A over B plus A over C. It would be incorrect to do that. It does not make any algebraic sense. So I can expand along a numerator, I cannot expand along a denominator. So if I have something like x squared over 2x cubed plus 7x plus 9, and that might be scary, and I might ask you to do something with that function, and you might say, oh, I need to simplify this before I can do something. It would be wrong for you to simplify it this way. You cannot say that's this. Or anything remotely similar to that. You cannot split the terms of a denominator. It does not work. So a lot of the rules we're going to have, they work very nicely on very compact terms like these, very simple terms. If you have huge things like this, odds are you're going to want to simplify it to very small terms. But don't be overzealous. If you have something like this, that cannot be done. You have to try something else. You need to be aware that you have to try something else. There are ways that you could potentially simplify something like this, but it requires something like long division of polynomials or synthetic division. And when we get to a point where that's necessary, I'll actually remind you about that. That's something you probably saw a long time ago. So I'll remind you about that when we actually need it. But those are this is a very common mistake that a student would make. Third major way we will combine functions is by composing them. You can say we make a function composition. Composite function is basically, it's a fancy way of saying you take one function, you plug into the other. We actually did some of this before. The notation sometimes is a little circle, which you saw in the last quiz. And basically what that means is you take f, and inside of the f you plug in g. Right? And this is called f composed with g. You can also call it f of g. Of usually means multiply in mathematics, but it does not mean that in this case. It's just a bad name. So this is called function composition. When you plug one function into the other, you say you've composed the functions. Let's do an example here. F of x equals square root x plus 4. Let's find the following. F of g, g of f, f of f, f of f of f. Composite functions are super important. We'll actually be dealing with them a lot. By the way, in the difference quotient, remember that was f of x plus h minus f of x all over h. This component here is actually you taking the composite function. It's like your f was the original function and your g is x plus h. Right? So you'll see them all over the place. So you need to know how to deal with composite functions. So it's something we've mentioned before, so I'll just write down how to do it. To compute, replace each instance of x in f of x with g of x. Right, so that's to compute f of g of x. Means everywhere you see an x in the function f, you will replace that x with the entire function. So let's just do the first one here. F of g is equal to f of g of x. What would that mean for these functions here? Yeah?
You plug the g of x into the x in the f of x.
Okay, and what would that look like?
Square root of x squared minus 2x plus 1 and parentheses and then plus 4.
Okay. So when you see something like this, here's the approach I'd like you to take, especially if you're shaking on this sort of thing. You realize that f of x is this. X you want to think of as a placeholder. Whatever goes in the parentheses here, you put it in this position. So what you want to do is just open a gap where the x would be. Right? And what are you going to put in that gap? G of x. And strictly speaking, it's not technically necessary to write this line down, but I would suggest that you write this line down. Especially until you're used to it. And then you go and you're like, okay, g, now I can just put that in, what that is. That is x squared minus 2x plus 1 plus 4. And at this point, I can combine like terms. That's x squared minus 2x plus 1 plus 4 plus 1. So that would be your answer. What about g of f?
That would be square root of x plus 4 squared.
Square root of, well, that means you're taking the f and you're plugging it inside the g, which means I would go to the g function, whenever I see an x, open parentheses, 2, open parentheses, 1. And what I'm going to write inside here is f of x. F of x equals, what I'm going to put here is what the f is, which is just this entire thing I'm going to write here. You can simplify this into x plus 4. And I can actually combine the like terms here. That's x minus 2, x plus 4, plus 5. And that would be the answer. What about f of f?
You would plug in all the, you just plug in for the, actually plug in f of x for every, in the f of x function.
So this is the square root of x plus 4, so that's gap plus 4. I'm going to plug in f. This is the square root of the square root of x plus 4 plus 4. The square root of the square root of x plus 4 plus 4. How do we simplify it?
I used parentheses to give each of them like a 1/2 power, and then you can use like power rules
This?
to make
Like
yeah.
that?
Yeah.
For-
Without and then you can add, or you multiply since it's parentheses. So you have the x plus 4 to the 1/4, and then plus 2.
X plus 4 to the 1/4 plus
2.
2. Is that okay? It's not
Is
okay.
it?
What's
Oh, I
wrong?
separated them. Okay, my bad.
See what I mean?
Okay.
You guys see what I mean now, right? I told you that basic rule day one. Oh, you can't distribute powers across sums. And I tell you this other basic rule, but when you have to do 2 at a time, you forget. It's very important that we go over it.
I was that one guy.
In fact, that's one of the really bad rules. That's the kind of one that gets you a 0.
I shouldn't be.
Okay? So be careful. Not to embarrass Nicole, don't be embarrassed. Please really respond, because I guarantee you that there were several other students in this class. Oh yeah, that's totally fine. It's not fine. I know sometimes it might seem like a waste of time that I'm going over this to you guys. I want to emphasize it's not a waste of time. You cannot just take a power and put on each piece. So something might look complicated, you might want it to not look complicated. So you do all sorts of craziness. Do not get lost in your emotions. The rules have to be obeyed. This is not okay. So in other words, you cannot simplify that. That would be the answer. If you go further, you get in trouble. It's important that we go over all this basic stuff. For those of you who are rolling your eyes at me, I know this, Jhevon. Yeah, okay.
Okay, I have a question.
Yes.
What's the difference between those last two?
Oh, none. I just remove the parentheses and all of
Okay.
retard.
Whoa.
It's kind of bad word. It's 2018. You can't say retarded. I'm too old for this. How would you do f of? Yeah.
So I would start off from your last one right there, and then just plug in another after x where the x is.
Okay. Yeah. So, in my earlier class, a student tried to do this all in his head and just tell me, oh, one big radical and then another radical, and they got confused about how many radicals there were. But you really just, again, want to take this from the basics. Think of this as f of x. And you think of, well, that's not much better, but yes, it kind of is, because what is f? It's the radical of a gap plus 4. What goes in the gap? What's inside the parentheses? F of x. And then you sort of just break it down. Okay, but what does this mean? It's an f with a gap inside. What goes inside the gap? What was inside those parentheses? An f. And then you plug it in, right? So if you try to do it all in your head all at once, it's super easy to get confused. So you might be doing something very basic, but doing a lot of basic things all at once becomes complicated. So you just break it down, one piece at a time. So now you can plug in that gap. X plus 4 plus 4 plus 4. And resist the urge to turn these into half powers and distribute the half on everyone, because that would be incorrect. So that would be. So yeah, I'm telling you, the mistakes I'm describing to you, you might think, I know not to do that, but trust me, when you're doing something while doing something else, you're going to forget all of those. You need to have these rules in the forefront of your mind. Okay. One last thing I want to do in this section, which I'm not going to go into great detail about this, because we don't actually use it unless we're like sketching a graph, and it's not going to be super important, but transformations of functions. This is obtaining new functions by manipulating pieces inside of a function without actually adding a whole other combining two functions. You're doing this all within the same function. So there are a few of these rules that are important, and they really come up when you're talking about. The really nice way to see them is a quick way to draw a graph or get a sketch to see a picture in your head, because a lot of times that is useful when it comes to mathematics. So things like, let's say f of x is a function, and c greater than 0 is a constant. So things like, what is f of x plus c? What is f of x minus c? What does that mean for a graph as a function? So if in a function you go and you replace all the x's with x plus a positive number, what does it do to the graph? Yeah?
Is it a horizontal shift?
Horizontal shift, what direction?
Positive.
Yeah?
Just the left, right?
To the left, right. So it's one of those things where when you're manipulating the x, things kind of work in the opposite way that you think it should. So if you add something to all the x's, you actually shift back. You shift to the left. And if you subtract something from all the x's, you actually shift to the right. The idea is because, for example, if in your function you're plugging in a larger input, your output kind of has to shrink in order to keep its original definition. It has to compensate for it. So this is actually a shift left by c units. So for example, if you have the function y equals x squared, that's your f of x. This guy is going to take that and shift to the left by c units. So this would be some, so let's say this is x squared, this could be something like x plus 2 squared. And this would actually shift over to the minus 2. Similarly here, this is shift right by c units. So if you have something like y equals x squared, and you're looking for y equals x minus 2 all squared, that actually shifts to the right by 2. This is y equals x minus 2 all squared. Right, so if you manipulate the x by adding or subtracting something, it shifts to the left if you add something, it shifts to the right if you subtract something. What if I add something on the outside? Right? Now remember, there's a difference between this and that. This is a composite function. I'm plugging in x plus c for each x value. This means I take the original definition of the function and then I add the c separately. What happens here? Yeah?
The function shifts upwards.
So here, whenever you're not manipulating the x, you're manipulating the y value, it kind of works how you expect it to work. Plus means go up, negative means go down. So this is shift up by c units. So that's if you have something like an x squared, then if you take y equals x squared plus 1, that actually shifts this guy up so that this small part is right. F of x minus c is a shift down. So you can go from an x squared to something like this, if it's an x squared minus 1, for example. So this guy covers horizontal shifts. This guy covers vertical shifts. Yes.
For the horizontal shift, that's going to affect the domain.
Not necessarily. It might. I mean, if your function is defined on the entire real line, then no, it won't change. But if there's a specific part on the x-axis that is the domain, that domain will shift with it. So it depends on how your function is defined. If f is a polynomial, that's not going to change the domain. The domain is still going to be all real numbers. It's all real numbers here as well as here. What else do we have? It's 3. Let's talk about horizontal stretching or shrinking. So here is, again, we're going to do the manipulate the x, but we're not going to add something to it. We're going to multiply by something. Cx. And here I'm assuming that, let's say c is greater than 1. What do you think is going to happen if I multiply x?
Stretch.
Yeah?
Function is thinner.
It's a shrink. Right? Remember, the x kind of does the opposite of what you think. Shrink by a factor of c. And this is a horizontal shrink. So, for example, if your function looks like, if your f of x looks like this, then if someone tells, and it goes up to 1, and then someone tells you, what is f of 2x? It's actually going to shrink. It will only go up to a half. Similarly, if you have f of, say, 1 over c times x, that's actually a stretch. Stretch horizontally by c units. So, again, if this is your f, goes up to 1, that's f of x. And someone asks you, what is f of x over 2? It actually stretches out over 2. So it will hit like 2 instead of 1. If you're on the outside, this is for vertical stretch / shrink. C is bigger than 1. Then yes, again, that kind of behaves in an expected way. You take the c times the f of x, that stretches vertically. By a factor of c. If you take 1 over c times the function, that shrinks vertically. Just one more thing for reflections. If you have f of minus x, what does it do to the graph versus minus f of x?
Doesn't it like reflect it over the y-axis?
Okay, so this reflects in the y-axis. So if your function is this, then that actually just reflects to become that. This guy reflects in the x-axis. So if your function is this, it will become that. These will be important later. We'll use pictures for a bunch of things, including when we talk about physics. Let's So knowing that's going to be important. That's all I want you to remember about your transformations, basically, just kind of a pictorial idea of what happens. So that ends it for transformations. And that actually ends what I need to talk about from 1.2. So now we have 1.2 also due on Tuesday. So 2 sections of homework due on Tuesday. Let's move on to 1.3. And that's all I need to We're going to talk about linear models and rates of change. Basically, we're going to revisit straight lines, what they are, and some ways that we're going to be applying them. Do you guys know that movie that it's recently out, or maybe it's almost going to be out, that has like Terry Crews and King Batch, and when he tries to infiltrate this fraternity or something like that? You guys know that movie? Anyway, there's a scene in the movie where it's like it's an all-white fraternity. They're all white kids, right? But his dad and his uncle robbed a bank a long time ago and hid the money in the frat house. It wasn't a frat house at the time; it was a crack house. But they renovated it and made it into a frat house. And to get the money, he pretended to join the fraternity. So he's this one black guy in the fraternity of all white people. So in this fraternity, they actually call their pledges slaves. And so the guy's like, "Oh, listen, you slaves are going to do this." and then one of the kids go, "Trigger warning!" And then he comes over and they all start huddling and he's talking about, "I don't think we can use the word slaves anymore." And he's like, "Isn't it more racist to change what we're saying just because there's a black guy here?" And then the other guy's like, "I'm so glad we're finally having this conversation." It's like, when I said retards and I saw her face, like, "Oh my god, you said retards." That's what I thought. Like, trigger warning, oh my god, okay. Can't say that word. Oh my god, it's offensive. Okay, let's move on. Linear models are, or linear models occur, I don't know how to say it, occur when we use straight lines to model a situation. This happens more often than you might believe. If you remember, one of the first examples I did in this class was Jhevon's hot dog stand. And we can actually, when we were modeling how many hot dogs I sold versus the price, it ended up being a straight line that described that situation, right? So that was me using what we call a linear model. I wanted to describe a situation, but it turns out that the best mathematical description was a straight line, right? So whenever we use a straight line to describe a situation, we say we've created a linear model. There is a situation that you can know that a situation, if I give you a random word problem, how do you know if the situation is described by a straight line or not? This is used if we have a function. So there's some rule that we want to describe, but it changes by a fixed absolute amount per unit time. Okay? So let's say I'm describing this situation and I can say, you know, after every month it will increase by 5. You know, or something like that. then it means a straight line. So one example would be something like a car rental service that actually charges you per mile driven is something that you would model with a linear function because it's changing by the same amount. So for example, a car rental service charges a flat fee of, let's say, $30 plus $2 per mile driven to rent a car. Describe the cost of renting a car using a function. Right? So this is an example of a situation that we will describe using a linear model. Why? Because there is a value that it starts out with. They charge you a flat fee of $30, but that fee actually changes over time or over some other variable. It changes by $2 per mile driven. So every time you drive 1 mile, it increases by 2. Drive another mile, increases by 2. Drive another mile, increases by 2. It's always increasing by the same value. It's always increasing by 2. Okay? There are other ways to, of course, increase. You could have increase by 2, then increase by 4, then increase by blah, then increase by blah. You end up with a straight line if you're increasing for every step on one variable, you're increasing by a fixed amount on the other variable. And whenever you want to describe a situation like that, it turns out that a straight line is always the best way to describe the situation. So here, I can say set C equals cost, X equals miles driven. Then we could write C of X would be equal to, how would I describe this function?
2x plus 30.
2x plus 30. So here, this is the flat fee. Right? So in a linear model, the value that you're starting off with will always be the constant, and that will, on the picture, end up being your y-intercept. This 2 here represents the amount, the fixed amount being added per unit x. Okay? And notice that you can tell that that is analogous to the slope. So in a linear model, that amount that you're changing by per unit time is actually going to be the slope of the line. And your starting point will actually be the y-intercept of your line. So that's an example of applying a linear model to describe a situation. And it's a very important thing to be able to describe. I think we'll stop there. So homework for 1.1 and 1.2 due next time, and we will pick up here and we'll revisit straight lines, and we'll talk about some interesting ways we can look at the slope of a line and start to segue our way into calculus.